So right now I'll be talking about CClyzer. CClyzer is a tool similar to Dupe, but it's targeting LLVM bitcode instead of Java bytecode. So basically C, C++. Does anybody know what LLVM is here? Is anybody who doesn't know what LLVM is? Haven't heard of it or anything?
What, you're going to tell us if we haven't? What is LLVM?
It's a compiler infrastructure developed initially in Illinois, University of Illinois, right? And acquired 2005, I think, by Apple. So those of you who have Apple should be most familiar with.
Why? It wasn't a company or something?
No, it's open source. So Apple supports it because they hired the main developer and then they put resources behind it.
Okay, so this talk will be mostly about how differences in the languages of C and C++ compared to Java translate to differences in pointer analysis. So how, essentially, how does C, C++ makes our lives more difficult to analyze it? You know, the crucial features, how do we handle them, and how the model of pointer analysis changes. So you will see basically a variant of things that you've seen in the previous days. Different schema, different relations, but it will be very similar. So, a few things about the LLVM bitcode. So you know of LLVM, but have you ever seen LLVM bitcode? Have you ever opened a file that has LLVM bitcode in it? No. Okay, so who have seen LLVM bitcode? Half the audience. Okay, so pretty much the main points of LLVM bitcode is that it's, compared with Java bytecode at least, it's a quite low level, it's a low level IR. It has main instructions, it lacks object-oriented features such as vtables, dynamic dispatch, invoke virtual, for instance, in Java bytecode, or classes, and it's quite, it corresponds mostly to C code. So there's a one-to-one correspondence with C constructs, but for things like vtables and classes, you have actually to translate them to lower level constructs. It's a strongly typed RISC instruction set, and it's pretty much the base of the LLVM umbrella project. So everything that of this infrastructure, like debuggers, the decompilers, and Clang, of course, which is the compiler of LLVM, uses LLVM bitcode.
So, George, was that a deliberate decision to not support higher level C++ constructs at the bitcode level, or it was something evolutionary that supports C first and then C++?
I have no idea. I don't know.
This project, LLVM means low-level virtual machine. Okay. So initially they started trying to make a virtual machine for machine code, but then evolved to be more of an optimization, compilation framework. It can do both things, but it shifted. So initially it was about machine code, running it on something like VM, JIT and stuff.
In fact, it's also to make it easier for hardware companies to write their own backends from an LLVM IR to ISA.
However, I think that the low-level virtual machine initialism has been deprecated. They don't use it anymore, but that was what it essentially meant. LLVM, I don't know. Okay, so here are the basic instructions of LLVM, the basic instructions that are relevant to pointer analysis. LLVM has a bunch of other instructions like integer additions, multiplications, and divisions, and same thing for floats, and just it's I think like something like a few hundred instructions. No, a few hundred, maybe 100 or something. But in pointer analysis, traditionally we are mostly interested in a very small core subset of those. So let's just look at them one by one, and if you're not sure about anything, just interrupt me. Okay, first one, the alloca instruction. So the alloca instruction just performs a stack allocation. So it takes a type as its operand, and it returns a pointer that it performs the stack allocation and returns a pointer that points to this exact memory location on the stack. Okay?
Can you move your pointer? Yeah.
This one here.
Yeah, just move it out of the way is what I meant.
Okay. Okay, next instruction. So we'll see more about the alloca instruction in the following slides and why it's needed, and a thing called virtual registers, but hold your breath. So next there's the malloc instruction, which is actually not an instruction, but we traditionally in pointer analysis we treat it this way because it's very important for pointer analysis, since when you encounter a malloc instruction, you have to create an abstract object, as you can guess right now. So actually malloc is just a function call, and it's implemented by the call instruction. That's the one before the end. But let's just take it for a separate instruction for now because we treat it differently. So malloc performs an allocation, but the allocation is a heap allocation. But that's not the only difference here. The operand it takes is just a number of bytes. So it's one of the few things in LLVM, at least, when we perform pointer analysis, that it's not associated with a type. Because alloca knows exactly the type of the allocation that it does, but malloc just returns an array of bytes, essentially. So then we have to cast it to the correct type. Okay. The next two instructions are load and store. So load basically takes an address operand and dereferences it, and from a memory location it maps back to another memory location, just what we know as a dereference. And there's the store instruction, which is the way to store something to memory location. So in source code, actually, okay, you can think of them like I wrote them. So that's the store instruction, and that's the load. Okay? Next instruction is the address of field. This is an interesting one. So this is essentially that expression over here. Can everybody see that? So it returns the address of a field. It takes an address operand, which must be of some complex type that has some fields, and just adds some offset to this address and returns another address, which corresponds to the exact memory location where this field starts, right? So another relevant instruction is the address of array index, which instead of a field index, you just have an array index. Okay. Next, we have a traditional call instruction, which takes a fn, which is just an operand that it's a function name usually, and the arguments, and it returns it. It makes the function call. It returns the result and stores it to v.
A function name or a function pointer?
Both. So
the general case is a pointer.
Yes. So in most of these cases, all the operands can either have constant values or they can have variables. So if you supply it a constant name, it's a direct call. You know exactly the function that it's going to be called, but you can pass it a function pointer, and this is an indirect call. Okay? And the last one is the bitcast, which is used, for instance, after performing a malloc instruction to change the type of the result. So this is, I write this as a no-op cast instruction because it doesn't actually change anything. It doesn't actually change the contents of the memory. It just transforms the type to be compatible with the type checker. Okay? Okay, so this pretty much is the core of the LLVM bitcode instructions that any pointer analysis expert should care to write. Yes?
Do you know how the template casts are handled in LLVM?
The template cast? No.
Because those are not just changing the type.
Yeah, but it will have something to do with RTTI, right?
I'm not really sure. I'm not sure.
But it's a C++ feature, so I think it will just go into the object layout, find some relevant field, and do some check on it. But
so you say that it's translated to a bunch of instructions.
Yeah, it's like everything else that is object-oriented feature. So now I'll discuss some of the crucial differences between what we've seen, the LLVM bitcode and Java bytecode, and why is it important and how it changes pointer analysis. What do we have to do differently? So the first thing is that the instruction that we saw in the previous slide, the address of a field. So if you think about it, in C, this is LLVM defines such an instruction because you can do such a thing in C. You can take the address of a field, but you cannot do something like this in Java, for instance, right? So it's complicated. It complicates things because what you can do is that suppose you have a pointer to some complex type, to a struct, so you can just take the address of a field, and then this is a regular pointer. So you can pass it on to some program, a completely different program point. It can reach another function even, and then you can load from it. So there's an indirection there. It's actually two instructions that in Java they're bundled in one. So that makes things worse for us. For instance, here you can see that if you have if you want to take the value of an expression p ROF, this in fact translates to two instructions. First, to an address of a field instruction that takes p and computes the offset to the exact field, and then uses a load instruction to get the value back. Okay, is this clear? Okay, so you can see why this is important, even if you just look at the IRs, if you contrast LLVM bitcode and Java bytecode. For instance, in Java bytecode, load and store instructions have one more operand, which is a field specifier. They don't just take an address. In Java bytecode, you must have a base object, then a field for a load, and you load from a specific field, and then it returns back another object. So the same thing stands for store. But that's the difference here. The fact that you can take the address of a field makes such an instruction irrelevant. You can just implement it like this, by taking just the address of a field and performing a normal load, like anything other regarding pointers. Okay? Not convinced? Okay, so as I say, in Java you can only allocate objects, and then you can load or store from a specific field. This is the only way that you can change memory, in the heap at least. So that's why they are ternary. When I'm talking about Java bytecode, sometimes I mean Jimple, because they're not really ternary per se in Java bytecode, because bytecode is a stack-based IR. So, but if you take the Jimble translation that we've talked about in the previous days, this is what you will have. Okay. So next difference. So if you write some C and declare some variables on your source files, and you open the bitcode files, you will notice that if you had, for instance, something like this, a declaration of just an integer that takes the value 3, then this changes. So P becomes a pointer to an integer instead. And there's an alloc instruction happening. So for every source variable, what will happen is that it will transform its type, it make it a pointer, and will just put an alloc instruction there. Unless optimized their way, but just don't think about this right now. So for instance, if you had just this thing here, which is a declaration and the initialization of P, there will be a alloc instruction. So the type of P here will be a pointer to integer, and then there will be a store instruction that stores 3 into this memory address. So why do they do that? Because you could have, if you had a variable P there in your source code, there could appear the address of P, like this in C. But with this transformation here right now, this can be just substituted by just P, which is exactly this, the address of P. Okay? Confused a little? No. Okay. So any subsequent assignments to P here would be just more store instructions that will take another value and store it in the same address. But these are not the only variables that you can see in bitcode. So since bitcode is a form of lowering, you will see all kinds of intermediate expressions being translated to more instructions that will be stored to temporary variables. So temporary variables are don't have names. They're actually things like that. There's numbers, okay? But as all local things, they're prefixed by the % sign. So temporary variables and the source level variables together, they are what we call virtual registers. So you can think of them as normal registers, but in fact the register allocation step hasn't happened yet. So later, if you can have an infinite number of virtual registers in every function. So when register allocation does happen, some of them will be translated to normal physical registers, and some of them will be spilled to memory. Okay? Another thing here is function pointers. No functions pointers in Java, but as I said to Yannis, you can have, as in every other instruction, in call instructions, fn could just well be a variable instead of a constant. So normally you don't use function pointers that much in C, but if you look at LLVM bitcode, and actually if you look at bitcode that was produced by translating C++ code, then you will have a bunch of those, because function pointers are the basic construct that is used to implement virtual tables and classes and dynamic dispatch. So we'll see exactly how that goes, but function pointers are the key here. Okay? So what this means is that a pointer analysis that has to answer queries correctly about knowing what function will be called at a dynamic dispatch call, and it will have to know something about the function pointer. Where does it point to what function actually does it point to? Or else it will lose precision. Okay. So as I said, in Java, you don't have function pointers. In fact, functions methods are not even first-class citizens. except reflection. So you cannot pass, in Java you cannot take a function and pass it as an argument, for instance, to some method. There are design patterns for that. And again, Java bytecode is much higher level. So there are instead invoke virtual instructions, invoke special, invoke interface, and invoke static. You have seen those. You remember them? I mean, invoke virtual is the standard instruction for implementing dynamic dispatch. So you don't have to specify in Java what the exact form of the vtable. You just declare something as a class and what its fields are and its methods, and then you just see an invoke virtual instruction, which will do the actual dynamic dispatch, but it's not translated to anything lower in bytecode. So there's also invoke interface, which does the same thing, but for interface types. There's also invoke special, which does not perform dynamic dispatch, and it's used for constructors and private methods, and invoke static for static methods. Okay, so final feature here is the constant expressions. Okay, so the definition is that a constant expression in bitcode is a constant value that is initialized with an expression using other constant values. So here's an example. Can you see this thing over here? This is a constant. This is a complex constant expression. Can anybody guess what this is?
An array of 5 bytes.
Containing what?
Containing 0. It's a vtable?
Yeah, it's a vtable. So here, these are function names. They are actually method names after name mangling, which happens with C++. So these are
5 pointers.
yes,
5
4
to
pointers.
character.
Yes, but they are just bitcast, like normal pointers.
So is the second one a method? The ZTI one?
No, that's actually not a method.
That's the typing, right?
Yeah, I think so. No, the last 3 ones are methods.
They're all bitcast to pointers to bytes. Right, so it
Yes,
doesn't really remember that it's a function. That
it transforms everything to just a plain byte pointer.
And there's no void star, so this is the most generic pointer you can have in a
Yes.
game.
Exactly.
Okay.
Even though I will be using some void stars later, but I will be lying. What you say is correct. There are no void stars.
But now we know.
Okay, so this is you can see the bitcast here. This is a bitcast constant expression. So pretty much for every normal instruction, there's a bitcast instruction. There's also a bitcast constant expression that does the same thing, but it cannot involve variables, for instance. So here, this is a constant thing. We know exactly where it points. It just refers to a function name, to a global entity here. So you can compose them in whatever way possible and create bigger constant expressions as this one here. So there's a constant expression, a bitcast constant expression, and this is a constant array expression. This is also another expression that just includes those things here. So that is pretty much what we will see as a vtable. So as I said, to be able to handle dynamic dispatch precisely, we have to come up with a strategy to reason for the contents of all those things, of constant expressions, with as much precision as we can have. Yeah.
The @ symbol, is it special?
Okay. The @ symbol is for global entities. So local variables, for instance, start with the % prefix, but global start with the @ sign.
Right?
Yes. Okay, so normally you use constant expressions in constant initializations. For instance, if I want to, if I can create an array in C or a struct and just write things here and perform the initialization for every or a subset of its indices. You have seen this, right? If it's an array of int, can do something like this. So constructs like this actually translate to constant expressions. This thing here will be a constant expression.
You can do the same for structure,
Yes.
but you have to specify the name
No.
of the field.
I don't think so. It's with the order that they appear on the source code. Okay, so in Java there's no such thing, and with Wish there was no such thing here too, because you will actually have to duplicate much of the logic that handles instructions. You have to do a similar thing for constant expressions. One could be tempted to eliminate them, but the problem is that, as I said, constant expressions are used to initialize global variables, for instance. So there's no function that initializes global data. They're just in plain instructions outside any functions inside bitcode. So you cannot, in general, just perform a compiler pass and eliminate every constant expression unless you do something which is not actually bitcode, something that doesn't actually run.
But you could eliminate something like this one, right? You could replace it with for assignment.
Yes, but what if R was just a global variable? Where would you put the instructions?
Can you do this initialization also in global space?
I don't know if you can do this exactly, but you can do things like this. Okay. So it was just to give you an idea of how things are different in C, C++. If you have a background in analyzing Java, you're more familiar with it. And so we'll talk now more of the high-level differences about pointer analysis. So another thing that actually changes a lot is the memory model that we compute. So for instance, look at this here. This is conceptually what is the product of a pointer analysis in Java. What dup computes. Can you see what's the analogy here? I mean, what corresponds to what predicate? So what is this edge here?
Var points to?
Exactly, it's a var points to. It has a source, a variable. So in Java, every variable resides on the stack. There's a clear distinction. So var points to, every row in var points to corresponds to just an edge here from a variable to a heap object. What about this one here? What?
Field points.
Yes, instance field points to. Did we call it field points to on the previous days?
We had field points to on some slides and instance field points to in the code.
Okay.
So we've seen both names.
Okay, so instance field points to takes an object and a field, and then it maps back to a set, or just every row maps actually to just one other object. So we can just represent it here with a labeled edge between objects, however. They have nothing to do with variables. So, for instance, if you had just something like this, a list of strings.
So the label of the edge is the name of the field, as it were.
Yes. So this would somewhere be initialized to a new linked list, for instance, And if it was a non-empty list, then we should at least compute an edge like this. So an instance field points to from the linked list by the head, I guess they call it like this, the field of some linked list that points to the first abstract object that corresponds to a node. So, of course, we would lose precision here, even in dupe, because if we suppose that there's only a single allocation site that allocates a node, then every concrete node object will be abstracted by just one abstract object, the one here. So the next field of this object will point to itself. This is because this represents more than one concrete object. It doesn't have to be a circular list. Is this clear? So of course every node should also have a field, I called it data, that points to the actual contents of the node, which would be other abstract objects here. Strings are also abstract objects, so it'll be something like that. So here, if we want to take just the first string out of this list, we could not be able actually to differentiate between all those. This would point to, after get first instruction, or whatever, it will point to every string that was stored inside the list, probably. So this is pretty much what we compute with dupe. It's an equivalent representation that just boils down to the core predicates, which are var points to and instance field points to. Okay? This should be perfectly clear. It's very important. So if you have any questions?
Just, so it's a detail. You said that you have only one abstract object for each allocation site.
Yes.
And we see two string objects.
Because there will be at different allocation sites. So,
okay.
Here, if there are two different program points with a different string, it will result in two different sites.
But if initialized somewhere else, the first string may point to both.
Yes. We could also have more than one abstract object here. It depends on the exact implementation of the linked list. If they actually wrapped the allocation inside a single method, this would be the case. Okay, but our model is quite clear here because we have variable objects that are things on the heap that point to, by var points to abstract objects that reside on the heap. There's a clear distinction. But consider something similar in C, C++. How does this change things? In C, C++, there's no such distinction. You can have the same, any object may be allocated either on the heap or on the stack. So these are the same kind of entities as far as pointer analysis is concerned. Is anybody clear on this? Okay, another difference. So let's talk about a little bit about these edges here that we see. So this is a dereference edge, actually. So the first string here is a stack allocation. So if you dereference this pointer, it will get you back to another allocation. That could be on the heap, it could be on the stack, it could be anywhere. But this actually is just a dereference edge in C, C++. But what about this edge here, the field edges? Are those clear? Could we always represent things like this? recall by the previous slides that we can take the address of a field in C, and also in C there can be an object that contains another object. So for instance, I could have a struct inner with some fields here, and an outer struct that contains an inner struct. The object layout is very different in C++ and Java in this case here, because in C++ this will be an outer object. I shouldn't write there. This is what we have in C++, right? The inner object is inlined inside the outer when I write this. Whereas in Java, I just have a reference. It's just a reference that points to the actual inner object. Okay, see the difference? So, why does this make? Why does this complicate things? Because, as I said, we can take the address of a field. So imagine that we have a pointer that points to the outer thing here, and then we take the address of a field of the inner field. So we had this, and then we had. Now we have this. So what should we compute with the pointer analysis? If we try to stick to the model of dupe, something similar, we cannot express something like this.
Is it because of array smashing, maybe? Why?
Now, what would I derive? What instance field points to would I derive? I mean, instance field points to in Java implies a dereference happening, a dereference here. Whereas an address of a field instruction just adds some offset, takes an address, adds something, an offset, and goes to an address somewhere near. But there's no dereference happening. Dereference in LLVM bitcode only happens in load instructions. Okay?
So you're saying that in Java the invariant is you point to the beginning of an object.
Yes.
Here you point to an object plus offset, perhaps. And
yes.
Sometimes you will know the offset, sometimes you will not know the offset.
Exactly.
But really, you cannot be guaranteed you point to the beginning of an object, just
yes.
where you started originally.
And actually, the result of any address of a field instruction will always point to, not always, but will point to the middle of some object.
Okay, so you will have to invent a different concept for what are the targets of point to edges.
Exactly. So what we actually do is invent new abstract objects that represent fields of abstract objects. So this is actually what we compute with CClyzer. So there's the my strings here. This is what we see in the source code. But if we look at the bitcode, this will be an alloc instruction and a virtual register. We'll just call them variables from now on. So we actually decouple the concept of the virtual register and the actual stack allocation. So these kinds of edges right now, these are CClyzer var points to edges, which is different from what we see in dupe. These are different kind of edges, just the same name. But when I say var points to edges, those are edges that originate from virtual registers. Okay, so this will always be trivial when we look at variables like that always take a stack that are the pointer returned by an alloc instruction. But you could also have temporary variables that would have more than one outgoing edge. So this makes not much meaning here, but we could have some other variable that would point to both here and somewhere else, theoretically. So that happens actually. Okay, so since we have a myStrings abstract object, we invent a new myStrings.head object, which represents the sub-object inside myStrings. Okay, and now
Well, yeah, but in C++, the head field would be a pointer actually. So, okay, it makes sense to invent a new object. If it was actually an object, like your example there with inner, would the inner object would be also a different object?
yes,
Okay.
yes, we would recursively compute every possible inner object. So here, if we have this abstraction now and invent new objects that represent fields, then field edges just are normal dereference edges. So this doesn't need a label. The label is just from the source of the edge. If the source is field sub-object, then there we have it. But it's actually, so these kinds of edges right here, we call them pointer points to edges. They're actually dereference edges. So there's only one of them. So there's the var points to edges here, and the pointer, the dereference edge is right here. Okay? So the same thing with the heap allocation here. So we have the new list node, so we invent a new abstract object that represents the data field of the list node. So here, if we had the address of a field and it pointed to this object, the variable that it was assigned to, it would just point to another abstract object, which is the field, the inner field of outer. Is this clear? Okay.
Now, why don't you have any edges from the heap back to the stack? You have those as well, right?
From which object? Here?
Well, in general, you could have edges from the heap back to the stack. There's
Yes.
no real distinction between stack and heap.
Yes, exactly.
All of them are abstract objects, and all of them can point to each other arbitrarily. So really,
So
the
that's
dotted
why-
line there between stack and heap is irrelevant.
That's why I made it a dust line. But it is irrelevant. You can have every combination between objects here. So this kind of collapses this distinction that we have in the Java bytecode between stack and heap objects, and instead we have a new line here which differentiates virtual registers from the actual abstract objects that include stack allocations.
Well, the boundary is not there for what can point to what other thing, but the first things are statically allocated, whereas the others are dynamically, right?
No, we record the information, yes, but so we can use it. But the dereference edges, the domain of those dereference edges, are just an abstract object to another abstract object. It can be either one, either on both sides. Okay, so let's look at more concrete examples. So from now on, I'll demonstrate some actual LLVM bitcode, some very small examples, and how we compute what we compute with CClyzer. I will not be showing any actual logic. I will just you'll be able to understand the logic. I'll be just presenting it in in graphs, just as I did in this example. So let's see the first example here. Okay. So let's look at this. This is a very small example, but it gives the point. So we have a global variable here, gv, and we have a func instruction that allocates something on the heap by calling malloc, a pointer actually. And then here we store to p, to the returned pointer, the address of gv, and then just return the pointer. So if we call this function from main, we return the result to pointer, and then we load from pointer, and x should point to gv, right?
Yeah.
So essentially, okay, something froze. Okay. So these are the abstract objects that we should definitely compute. We have this. Okay. This here is this stack allocation, and there's also the heap allocation, which comes from malloc here, and then after calling main, there will also be these two stack allocations. And of course, since we have a global entity here, a global variable, we also create an abstract object for these two, gv. Okay, so the first instruction just does this simple thing that p, when dereferenced, will point to the actual heap allocation. So that here is the outcome of the store instruction. So whenever we have a store instruction, it actually computes, it gives us a new dereference edge. So p pointed to this here, so after storing to it, when dereferenced, when this allocation here is dereferenced, it should point back to gv. And then by seeing the interprocedural flow from a main, where main calls func, pointers should also point to the returned allocation. And then by loading from pointer x, x should point to gv. So this is what we have to compute, right? Does anybody disagree with this model here? Any objections? Questions? Are you lost? Kind of.
Too many questions.
Seriously, give me one question.
No, this seems pretty straightforward. So,
Okay.
what's the point is really?
Okay, so here's the actual bitcode that we'll see after compiling this source code. You can see the alloc instructions, call instruction. There's a bitcast, of course, because, as I said, malloc always returns an array of bytes. So after taking p, we have to, after calling malloc, we have to disguise it to another type. And then there's the store instruction. So is this translation clear? Can you follow through it? Pretty much.
So you have to actually specify that the variable is global in bitcode.
What do you mean that you have to
You have a
specify?
keyword global.
Yeah, there's a keyword.
So I could write my bitcode file where global will be used inside a function, for example?
Looks like an allocation of sorts.
No, that's a good point. Yes, so you can see here that GV was of type int, but it's actually translated to a pointer to int here.
Yeah, but I would have that instruction inside the method, right?
No,
Why?
you can have global inside the method.
No, I could. I mean, if I would write the bitcode myself, would that be valid
I
bitcode?
guess it will be violating some rules.
You can have a static inside the method, but in fact inside the function, but it's going to be in fact a global, right? If you have a static.
Well, not with the same name. You could have two statics in different methods that would have different names.
Yes, I do.
But there's nothing
they
about
can
name
translate
there.
it to global.
There's nothing about name there. The way I understand it is there's a global pointer at GV, and where does that point to? It points to the 0th global that I will allocate in the static region.
Yes.
So if you had something with the same name, who cares? It's going to be the first global, the second, the third. The name is irrelevant.
Anyway, so I'll just show what do we compute with for every instruction, how do we handle every instruction, and how this corresponds to the model that we desired to have. So first things first, here we compute again a concrete, an abstract object for GV, and then the first instruction, when we see when we encounter an alloc instruction, we construct a new abstract object that corresponds to this abstract object allocated here in the virtual register, and then add the var points to edge. That's the trivial handling of alloc instructions. Just create a new object, a new abstract object, and add a var points to edge from the virtual register that's assigned to the object. Okay. So next we have a malloc instruction, another type of instruction. In this case too, we create another abstract object, a heap abstract object this time. You cannot see this here, but they are actually distinct. So there's this abstract object corresponding to malloc, and then just like before, the virtual register 1 points this abstract object. Okay? Bitcasts do nothing actually, so they just copy points to sets. Where did 1 pointed to? Just this object. So after a bitcast, we should just copy all its outgoing edges back.
So doesn't the site of malloc matter? You need to use context sensitivity to distinguish the site of malloc, or
No, it's just because I have one single malloc I represent like
okay.
this.
But otherwise, by default, you treat malloc
Yes.
context sensitively. You take the
Yes.
instruction that calls it.
Allocation side abstraction, just as in Duke. Yeah, the only reason I write malloc is because there's no other malloc here. Again.
Do you do the same for realloc, etc.?
Yes, realloc and calloc are all treated the same. Okay, so after this store instruction right here, how do we handle store instructions? So as I said, store instructions have two operands. This actually stores 2 to P. So store instructions actually introduce a new dereference edge. We call that dereference edges are between abstract objects, but what we have here is virtual registers. So first we have to overcome this level of indirection and get the actual objects that the virtual registers point to. So here, this is where P points to, and this is where 2 points to. So after 2 to P, after storing 2 to P, we just get this edge here. Is clear? Okay, and then similarly for load, where does load, we must again go over the virtual register. So the virtual register points to this abstract object here, so load actually does a dereference. So we have to follow an edge like this. These are not dereference edges. So from P, we can get to P here again, and then back to malloc. So this object here will be assigned to 3. And then finally, we have another store here, GV to 3. So GV, as I said, is a global variable. Just as we have decoupled the concept of a virtual register from the stack allocation itself, we do a similar thing with constants. So we decouple the actual literal, the GV literal here, with the global allocation. So this is a new type of edge. A constant points to edge, if you want. So the GV literal will point to the abstract object. The difference with constant is that never can a literal point to more than one abstract objects, and to the single object that it points to, it will represent just one concrete object.
So why do you need to do that? If it's 1 to 1?
What do you mean?
If the literal GV always points to that object and that object is the literal
You could have a constant expression here, for instance. So it's the same logic with constant expression. So GV could be inside a bitcast constant expression, for instance. So you would have similar logic that propagated the pointed to object from inner constant expression to larger ones. But then everything is the same. So we can treat the story instruction universally, regardless if we have constants or constant operands or variable operands. We just do the same thing. Just follow one edge from either the virtual register or the constant to the actual abstract object. Go, yeah, to the actual abstract object, and then if we have a store, just add the reference edge between those two objects. It's the same strategy. Okay. Okay, so this just after handling main. There's not much different here. It's just interprocedural logic is handled the same way as in dup. We just handle them as assign instructions. Just same thing, and assign instructions just copy their points to sets. So this is pretty much what happens. And those are all the temporary variables introduced by LLVM bitcode. So this will be the final thing that we compute.
For method calls,
Yes?
you should have a rule about virtual calls, but you should also have another rule for function pointers, right? A similar one, but different.
Why are they different?
Because in the first you have to do resolution based on type, whereas for the second you just care in which function objects the pointer may point to.
So what we do is that we track the function pointers correctly if they come from a C++ translation. So we know exactly. So in the following slides we'll see that this uses array sensitivity. So you don't need to know anything about types or, as you say, classes and things like that. You just have to follow pointers correctly and reason correctly about.
Those are just going to the vtable and.
Yes, and vtable is just a global array. So we know exactly what it points to at each separate index, and then it's just a normal function pointer thing. Okay, so that's what we wanted to compute. Fortunately, it's the same. Okay, so another simple example about fields here. So Suppose you have a struct type, which has just two fields, an integer and a pointer to integer. Okay? And you had a code like that, just an alloca instruction. So this thing here is the actual address of a field instruction. So both address of a field instructions and address of array indexes are called get element pointer. It's just an instruction that does anything. It's the single instruction that you can use to compute any kind of offset, but it doesn't do any dereference. It's not a load instruction. It just takes an address, it goes to a relative address with some offset. So here, because x, this is the index of this field. So this just means just go to the address of the second field here, and then store to this address. Any questions about get element pointer?
So what's 0 there?
0. Okay. So get element pointer 99% of the times has a 0 index. That's because in bitcode, whenever you have a pointer type, it assumes that the pointer type may point to more than just one field. Yes. So if you have a malloc instruction that allocates 5 objects, or a malloc instruction that allocates 1 object, it treats them the same way. So in essence, this says that I don't know what x is. X could be an array of things. So go to the first element that x points to.
So if I had an array, p brackets 2, there would be a 2 there instead of 0.
If it was allocated via heap, dynamically, yes.
Because it would be translated to p plus 2.
Yes, exactly.
So in other words, if you have a temporary variable that's an array, that's a pointer to int, it's really interpreted as a pointer to int array.
Yes.
Always.
Always.
So they are not arrays. There are no arrays in C. They're just pointers.
Right, but in terms
there is
of
no strict array type.
However, in bitcode, there's a distinction between array types. There is an array type which is different from pointer type. So, for instance, if inner object there, it could be an array type, which is different. It's no pointer type. It doesn't need a dereference. So it could be an array inside another object.
Well, there are array types in C.
Well, if you malloc one int or an array of one int, it's just the same thing. There's no array.
No, I mean the size of
the
it
link
is
that I sent you a few days ago
just
from Linus.
Yes, and that was if you pass it to a different function. But inside the allocating function, size of an array is different from size of a pointer.
If the array is static.
If the array is static.
Yeah, I'm not talking about static arrays.
But the point is, there is the concept in the compiler. There's a concept of an array type. I mean, if you do a type def and talk about an array type, it's a different thing from a pointer. There is the concept statically. How it gets translated from one to the other is a different story.
Okay, so let's see how this here is translated. Not translated, actually. What's computed. So as before, these are the objects we compute. So we have the virtual register of x that points to x. Now I will write x0, which is actually the same thing as x. But actually we do have indices for the first 0 index. But those two are x, and even if there was no 0, it would mean the same thing. Think of it as the same abstract object. So as soon as we determine we know what the type of x0 is. It's just a struct of s. So we can create an abstract objects for each of its fields. So this is the f0 for this field here, and f1 for this field here. And then the get element pointer instruction just what it does. It follows the indices and goes to the correct abstract object. So getElementPointer will always return you the abstract object, an abstract sub-object. Okay? And then normally, even if this was an entirely different function, if this was returned here and the store was a different program point, this could well be computed and establish this edge here as before, from the field to GV, which is like an instance field points to in Java, in dup terminology. Is this clear? The handling? No?
So you create new abstract objects for every possible sub-object of an object.
Yes.
So allocation sites like alloca that have a known type or malloc that have a known size, they create initial abstract objects. And then for all constant offsets, you go in and allocate sub-objects, create abstract sub-objects.
As soon as the type of an abstract object is determined, we, at the spot, we create all sub-objects.
What do you mean by all sub-objects? All the sub-objects that the type system allows?
Yes.
How about arrays of indefinite size?
So
I have an array and I don't know its size. It's going to create an infinite number of
sub-objects.
sub-objects.
It won't be inside your object. Inside your object, you just have a pointer to some other place.
So for arrays, actually, what we create are abstract objects for all the indices that appear on source code.
So all get element pointers.
Yes.
Different instantiations.
Exactly. So if there's just an array index of 3 and 5, and there's no other constant that is used as an array index in the source code, we won't create abstract objects for them. We actually do it a little bit more fine-grained by associating array indices with an exact array type and just create sub-objects for indices for this given type, but this is just an optimization.
Now hold on, what do you mean by array type? Int array, for instance?
No, so you could have like different array types, and getElementPointer tracks types, so it knows exactly that this index here. Suppose this. Let's go to the next slide.
But
so
a type is int array, for instance.
Yes.
Isn't that? So all int arrays in the program will be considered the same type.
Well, I think the size changed the type.
Yes, different sizes have different correspond to different types.
It's an array of 5 elements and it's an array of 10 elements.
So this is the type. This is an array of 100 pointers to integer.
I allocate n bytes, and n is completely unknown to you.
Okay.
And then I allocate 10 bytes, 100 n bytes at 10 different points in the program. 10 different allocation sites, all unknown sizes. At the first point in the program, I go to constant address 5. I do getElementPointer, treat this as an int pointer, and go to the 5th element, and just some field under that maybe. The second allocation site, I go to the 7th element. The third allocation site, I go to the 17th element. Are you going to create, I go to a different sub-object for all 10 allocation sites. Are you going to create 10 different sub-objects for each of the 10 allocation sites, just in case these are aliased? So any constant reference that appears anywhere in your program, you apply it to all arrays, all objects of compatible types, to generate the appropriate abstract sub-object.
Yes.
Okay. That's what I'm getting at, because that's an interesting concept. But that's probably wasteful, but it's sound. You create all the possibly interesting sub-objects.
Yeah.
So if an object had like 5 integer fields, you would create 5 sub-objects.
Yes.
So you don't filter out like primitives or...
No.
Okay.
No filtering whatsoever. So, as I said, we follow an array-sensitive approach. So, the same way we handled field indices, we can handle array indices. So here we create this abstract object. X0 is the same thing, just forget the first index. But the same thing will be computed. But this is not entirely correct, but because you can see that in some cases you can have an index, when you have array types, actually, you can have an index that is not a constant. So what do you have a variable? We have no integer value information. We don't compute anything like this. So what we do is we compute a separate object, a star sign. So like an unknown index. So this one here and this here, those are different abstract objects. But if we don't connect them somehow, it wouldn't be very sound. Can you figure out why? Suppose I have something like this.
Well, everything that goes in 0 has to go to star. Well, not, yeah, and the other way.
If I load, let's see, just X. So this thing here will be assigned to this abstract object. But what if we load from I? Shouldn't we consider this thing here too? Because I could as well be 5. So those different abstract objects, whenever there's a star, there's a connection, a possible connection with other abstract array index objects. So that's what we do. We actually define something like a partial order. So you can think of a relation that it's something like pattern matching. So if there exists an edge from a node to another, it means that you can have the exact same thing by substituting any number of constant indices with star. So this is just a partial order here. And we actually compute the transitive closure of this. So there would also be an edge from here to here, here to here. So this is a more generalized abstract object than this one here. So when what we do is we copy the points to sets. So the point to set of this node here will always be a superset of the points to set of any of its parents, of its parent actually. So we actually copy the points to set of this node to that one. And then when we load from an instruction, when we load an instruction and we are at this abstract object here, we have also to take into account the points to sets of those two objects, but we never merge them so that we can differentiate between those two objects. Those have distinct points to sets. We never merge them. We just take them into consideration when we at load instructions. That's the trick.
If I have x of I gets x of j, and I have a few constant indices as well, shouldn't all those sets be identical? Like x of 5 should point to also whatever x of 7 may point to.
Will one it point to after performing the actual pointer analysis? If you have such an instruction, this will be by what you get. But if you don't have any such instruction, then it could be that the points to sets are distinct, are not the same.
So yeah, but if there is a a circle from an array to itself, or are they direct or indirect, then having the constant values as well is just a waste, right?
Yes. If there's a circle, it's a waste.
So have you measured in practice how often you have cycles like that?
No. But
Because for a flow insensitive analysis, I can imagine that this distinction really doesn't pay off many times. Oftentimes it may not pay off.
So the main way it pays off is for analyzing C++, because this array sensitivity characteristic is exactly what you need to be able to differentiate between different slots on the V table. So just with this one here, we can be able to correctly match reason about a dynamic dispatch.
Okay, so you're basically saying I'm wrong. Even for a flow insensitive analysis, this is very useful because
Yes.
you very rarely have the cycles that George is suggesting.
I don't have any
high.
actual measurements to give you.
But you're saying that
Well, it's
without
not
this,
that you have them rarely, but that you have cases where you actually need the information
yes,
that are useful.
right. You have very important cases like V tables where you need, where this gives you more information.
For V-tables it's easy because they are globals. You can just say, I only do this
And
for
they are
globals.
internally, right?
So
Yes.
you
So
can
you
just
wouldn't have the problem.
safely restrict your code to only apply this for globals, and then the rest of the code doesn't get problematic cases.
Yeah, yes, but it could pay off even for non-global things like an array initialization to a local element or something.
But it's interesting to actually measure whether it costs more than it gives back if it's not applied to
Yeah, we will
globals.
do an experiment and just applying it on global objects and see how
So,
things different.
George or Yanis, do you have any insight if this is useful in Java? Do you think that it's common to have constant indexes in Java?
I doubt it. I mean, you saw that the people in Australia did that for reflection. And they did that by changing the preprocessor of do, like the suit fact generation to create static arrays used for reflection to have specific representations of those objects. And it may have paid off in their case for reflection, but we got similar benefits with different analysis, with a use-based analysis for reflection. Other than reflection, I cannot think of many cases where it's really crucial for Java to distinguish constant locations in arrays.
Yeah.
But it's possible, but we haven't seen it.
Okay. We have mentioned it already, but just to clarify, when do we create abstract sub-objects? As I said, there are two cases. We have a struct type, which includes class types. We exhaustively create every possible field sub-object as soon as the type of the base, which is of struct type, is determined. Whereas for array or pointer types, we consider only indices that appear on the source code. Never create new indices, because although we could, if we have something like p, which is a pointer plus equals 4, we could create new, but we probably would never terminate. So we never do that. So in most of the cases, we have the allocation types, which are needed to create the sub-objects, are mostly available at the allocation site. So for alloca instructions, when you do a new object in C++ on the heap, new allocation, or pretty much that's it. But what if you have in malloc instructions or calloc, realloc, anything like this, you don't actually have a type. So another trick we do there is that if we don't have type information, we track all the bitcast instructions that this object flows to. So suppose you have a malloc somewhere, it gives you back an array of bytes. This won't ever be useful, so probably there will be some instruction, at least one instruction, a bitcast, that will transform it to the actual type. So we track those types and create new objects with type information that share the same points to sets, which is...
Can you show this in code? Because this also gives us an interesting opportunity to talk about something else.
Okay. I write it like C, but these are equivalent instructions that bitcode will produce. Okay, so we have an abstract object that corresponds to this malloc instruction here, but we don't actually have type information, just the most generic thing that you could have, a byte array. So, but probably it should have a type, which is what is in here, but all this this expression actually is doesn't exist on LLVM bitcode. It's replaced with the actual constant. So what we do is we track these things here, the pointer that is being casted to. So this will be an abstract object that will eventually flow to this one here. And by associating it with the type in the bitcast, we can create a new abstract object that has this type information. This could be something more complicated, like a struct type, like outer. This could be size of outer here. So whenever we do that, if it reaches this point and it creates a new object with outer type, if we had like outer, then the new object with type information will be able to create a sub-objects of outer, the field sub-objects in this case.
So now let's get back to the word eventually that you used. How eventually? Like how far can these two statements be?
So the only place that they're filtered are our get element pointer instructions. So get element pointer instruction applies type filters. So when you have an abstract object that doesn't have type information, like the one returned here, and there's a get element pointer in between, this will be pruned. It will not be considered as a possible object for base.
Well, sure, it's not going to be considered a possible object for P2 there. Is that what you're saying?
No, there's no get element pointer here.
Okay.
But if by some source of imprecision this object somehow made it to another get element pointer instruction later and used, you can have the same variables, let's say PA, which is an alias, something that will point the same thing, and then some indices, then no sub-objects would be created here. Because you wouldn't have, this would not match the declared type of get element pointer. That's just what I'm saying.
So basically you're saying the analysis is not sound.
Yes,
There may be objects there.
that's another way to say it, yeah.
There may be objects that you're not tracking just because you cannot tell what their type is. Okay?
Yes.
But you find out what the type is when you find a bitcast. Where can this bitcast be relative
Anywhere.
to a malloc? Anywhere.
Yes. We just rely to the pointer information. I mean,
So you propagate some dummy object, some abstract object that's
Exactly.
not usable otherwise. You propagate it everywhere. You let the points to analysis.
hoping that it will reach the point of the
bitcast.
bitcast instructions that actually create the correct objects that will make it further.
So that's exactly the same thing that we do in Dupe
Yeah.
with reflection analysis.
Yes.
And that's why I wanted to bring that up. Because that's the use-based reflection
That's a
analysis.
shameless plug.
Yes, but I'm not sure I will get the chance to talk about that. And it's a standard, it's a useful technique.
So George, you will create objects even if the cast should actually fail, right?
I'm not sure, Jack. I have to check that out.
Well, if I allocate something that's only 4 bytes and I cast it to a double,
So, whenever I have a malloc instruction, it is marked as a dummy object. So I know that only this kind of allocation objects should create a new object with type information. It's not like a generic treatment of bitcast.
no, I don't mean for every cast that you have. I mean if in my code I have a cast that should actually fail, if it's the wrong type to cast.
But how would I know that it would fail statically? I mean, the
No, I
malloc.
don't mean that you can do something.
Oh,
I mean
yeah.
that there you will create
Yes.
objects that should
So
be
if there
there.
was a malloc cast of 5 bytes and it just flowed to a bitcast that actually declared the type of 100 bytes, yeah, this would fail.
Yeah,
but
I
would never.
don't say that you should handle this. I'm saying that you're assuming that casts are correct
Yes.
in order to help you.
I'm doing another approximation.
Well,
in
it's
this
the same
direction.
assumption that we did in reflection.
But it is also important to point out the unsoundness. This is one of the very few places that the analysis will be unsound. It will not point to a superset of all possible dynamic objects during the execution of the program.
Yes.
And you're doing this purely because otherwise your analysis would not scale too well. So it's for engineering reasons.
Yeah.
So
I
you
mean,
will miss
I could
actual
probably-
program behaviors.
I could probably derive new objects for every possible type, but I'm doing it to scale, hoping that for actual programs, it will not be a source of unsoundness so much, that actual programs behave well. And I think that if a program behaves well, this pattern is enough.
Well, is it guaranteed that something will be bitcast before being used? That the result of a malloc will be bitcast? Not really, right?
It could be used. So, for instance, there's another rule that I didn't show here, that you could transform pretty much any object as an array of bytes and then do a get element pointer which matches the declared type, which is an array of bytes, and go to the 7th byte, for instance, and store something there. So you could do that. I have a rule that actually matches these things, because this is actually something like that actually happens in C++ translation for dynamic dispatch.
But there's a bitcast to get this array of bytes.
No.
So the point
no,
is
there
it really unsound or not? Is there actual use of these objects that you're missing by expecting that the result of malloc will always flow to a bitcast?
I mean, the soundness of this treatment generally depends from the rest of the analysis. If the object doesn't make it to the bitcast, it will be unsound anywhere. So they are pretty much.
Why is the rest of the analysis going to miss the fact that the object will go to the bitcast? The rest of the analysis should be sound, right?
Pointer arithmetic, for instance, any low-level C thing, you could mess things up.
If the original source code messes things
Yes.
up, your
I mean, but
analysis, that's why
it's
it's
not
sound, I
guaranteed.
think. Because It cannot enforce soundness on an unsound program. How to call it?
No, but I mean, for programs that conform to the C standard, what can go wrong? What's missed? I don't see the point. I'm not talking about disguising pointers or anything.
So you said in the first slides that LLVM IR is strongly typed. Bitcasts are there to guarantee the correct types, right?
Yes.
So bitcasts are no ops that just guarantee that from now on I have this type.
Yeah.
So nobody can violate this thing.
No. At this point of the program, no.
Okay. So your problem is before the first bitcast, right?
So the possibility of the actual object not reaching the bitcast instruction.
One, at least one, because after the first bitcast, you're safe.
Okay, so another thing, you can also have union types. So I don't know if this could you use an allocation with two different types? I mean, I guess, is this compliant to the C standard? I'm not sure. In what cases it's not.
It has to do. What?
Say it again.
If you just malloc a number of bytes and use it as a type, let's say it's 100 bytes, and there are two types: type A, 100 bytes; type B, 100 bytes also, and then you perform some operation. Use it as cast it to a type A, do something, then cast it back to void star, and then cast it back to type B and do something else.
Yes.
Yeah,
I mean,
we'll do that.
this is possible, right? So I will miss that
And I think
because I would consider two different objects. Each abstract object has at most one type. This is what a design choice, if you want.
Throughout the life cycle of the analysis.
Yes.
You cannot change it.
An abstract object is associated with a single type. So
During its whole lifetime, that's what I'm thinking. You cannot change it.
Yes.
It's done, but
you cannot change it now
Yeah.
during its whole lifetime.
so. You mentioned union. Are you doing anything special for union?
No. The only thing.
And I think in unions you don't even have a cast, right? I can store it to a field of some time, and I can read from the other field of the other type. And I don't have a cast there
To be honest, I haven't even looked at what is the bitcode produced
for union.
with union types, so I can not really give a.
There must be a bitcast at the bitcode level.
Why? You don't need it.
I mean, just the assertion it's a strongly typed intermediate language means there's a bitcast. If it's a strongly typed intermediate language, there's got to be a bitcast.
What's the problem there? You are guaranteed that the address that provide can store both types.
Well, but an expression has a unique type. at any given
And that
point.
depends on the
I mean,
fields
it's
that you're using to
compatible.
read the data back. But you don't need a cast there.
I don't think otherwise you would have bitcasts anywhere. I think they probably just add a bitcast.
I'm not
When
sure.
you read it as one or the other, they add a bitcast and then they do it. That's what would make more sense.
I'm not sure.
We would test it.
So,
although the IR is strongly typed, doesn't mean that
The
source
language is
code,
not.
that the language.
So another example again is that I could be incorrect. Suppose I have like something like this, okay, and P is a pointer, and a pointer to an array of bytes. So I will never create P8 sub-object if there's no 8 in the source code, but I could definitely write a program that does something like this and then store to this instruction. Then I would lose some information, right?
Why would you lose some information? It would still go to P star. It would still go to the star. You wouldn't have a concept of P8, so of course you wouldn't know anything about P8.
The constant 8 could still appear in the bitcode though.
But if it does appear in the bitcode, then there would be the abstract object from 8 bytes from the begin, 8 words from the beginning of the P array.
Yeah.
Okay.
I'm
Yeah.
not sure. I have to check this out. See
Yeah, but
what actually
supposedly
happens.
you introduced constant indexes to improve performance, precision. So the star index should catch everything that it would catch in the previous analysis.
Yeah, but there's no actual variable here being used. So it will not actually flow to the P star. There are two get element pointer instructions, both with constant indices.
Okay.
So there will be like this. Suppose that
So then you would only assign to P4.
yes.
Yeah, but you
Okay,
would
but
assign
that's-
P4 2 times, and when you are reading something from P, you are and using star, you are reading whatever is stored in P4. You are storing the wrong things in P4, but everything is stored there.
But that's very unsound, it seems.
Why?
Because nothing should go to P4, and maybe those instructions are in a loop anyway. Maybe you store at P4, P8, P12, P16, P20.
Well, the actual
But that-
information
but-
that you have is
but
P star.
At
And
that,
P
at
star,
that point,
But George is saying there's no P star.
but at that point, it's flow insensitive, so you will not actually know that. After the first instruction, P does point to P4.
So how is there no P star? P and P star are the same thing. Everything that's going to go into P4 is going to go to something more general as well.
yeah.
So if
Let's put it differently. You have P plus equals 4, P plus equals 4, star P gets some new object. And then somewhere else you have P of 8 is read. Won't P of 8 see that new object?
you will see that, yes.
Okay, so there is some concept of P star. I don't know if it's called P star,
So
but there's going to be some concept of this goes.
so a star expression, a star sub-object is introduced only when there is a variable index in get element pointer. So if can I write a program that has no such index?
Well, but
Well,
there's
that's
got to
wrong.
be some concept of this goes inside some location of the P array. Or not. You just told me that I can read from P8
Yeah.
the thing that I wrote by doing P plus equals 4, P plus equals 4, and star P gets something.
Yeah. Okay,
P
but
star should always be there. It shouldn't
But-
be introduced when you have a variable.
maybe so. I mean, this is right now the only time when I introduce P star is when you have a variable index.
Yeah, maybe you
But
should.
the
always
point
have-
is, this is something to look into and see what the soundness guarantees are and where we're losing either soundness or precision, and know what we're going to get in either case.
But I mean, the way that you would catch the pattern that you said is that there's another rule for that when you have an abstract object, suppose P4, and this flows to a get element pointer, a gap x. So suppose that x points to here, and there's also 4, first index. If there is a constant index somewhere else in the program, so which means that there would exist a P8 object, it will be created by another completely different instruction, then it adds those two indices here, and then it returns this one here. So if the addition of those two indices produces something that already exists, then it will compute it, but it will not compute a new index by an addition.
Okay,
That's how
so
you
you're
catch
doing
what you
all
said.
possible combinations of constants
Yes.
and then give another constant. And at the same time, if you have a variable expression, you introduce p star.
Yes.
So you handle soundness in these two ways.
So, George,
Okay.
if you have, so P gets the address of A4,
Yes.
and I store something to P1, is that going also to A5?
I think so, if 5 exists.
No, 5 doesn't exist.
No. If 5 doesn't exist.
Does it go to A star?
If there's just constant indices being used, no.
Then you're missing information.
Yes, I know. I'm pretty certain that I will miss information in this case and in other ones too. But I think that it will be inevitable when trying to. I mean, I will definitely be going to miss some things when trying to.
Yeah, but if you handle star
C.
as a top, as a superset of everything that you have constant indices, I think that you would catch most of these.
Yeah. Actually, I have to check that out because I think I have. Maybe take it offline because I think I have some other rules so that could be performed something like what you say. If there is no such index, add to star index. Maybe I have something. I'm not sure because I mean, so this part of the logic is the most complicated one. It's a file called field sensitivity, and the other thing is pretty much simple. The core logic is very similar to dup, so it'd be understandable. So we'll look at it tomorrow, but okay. So, final note about C++.
Can I ask something
Yeah.
before that? So you said that you are doing special handling of malloc.
And calloc, realloc.
Yeah, are you doing special handling for other methods that would change the points to information, like memcpy?
memcpy I do, yeah. There's a whole different file about handling memcpy. Okay, so as I said, C++ things are translated to low-level constructs, and the previously discussed techniques all aim to be sufficient to reason about C++ programs. So the array sensitivity that I've shown you is a step towards this direction. So let's look at. So this is just you don't have to follow through it. Just to give you a glimpse of how actually what happens with C++ code is you will have like a type here with the first object, the first field being the v pointer, and then suppose I allocate an object of class B, and then I just these instructions here are dynamic dispatch. This is what gets produced. So first we bitcast the pointer to appear as the actual field of the v pointer, and then load from it. So this will take us back to the v table, and then we go to the exact. We have a get element pointer instruction that goes to the exact array index, which will, for dynamic dispatch, it will always be a constant index. And we go to an offset of the v table, and then we load again to go to the actual function. And then we call it with a variable operand. That's what happens. And from the previous techniques, this is handled correctly. So B will point to this here. 1 after the bitcast will also point to both objects. So whenever you have the first field of a struct has the exact same memory address as the containing struct itself, so it's an alias. The two objects are alias, so they have the same points to sets. So this will point to both. And after the first load, it will point to the v table. After the get element pointer, it will point to the exact array index, the second slot of the v table, and then by dereferencing, the pointer can know exactly what instruction gets called. Yeah.
So in the beginning you said that cast is actually a no.
Yes.
Is that true in C++?
What cast? Bit cast. There are other types of casts too here.
Well, I mean the standard cast that you have in C.
That's going to be translated to a series of instructions on the bitcode.
So the bitcode will have will handle the adjustment of the pointer. Okay.
Okay, so that was it pretty much.